Okay, so in this last lecture on heaps, we are going to talk about heap operations. And specifically, we are going to talk about how to insert an element into the heap, how to delete an element from the heap, how to quote-unquote heapify any given array, and then we are going to combine these into an algorithm for sorting called Heapsort, and mention a very important use of heaps called priority queues that you will study more in your data structures class. All right, let's get started. So the first operation is how to insert. Okay, so suppose you have a heap. Let's call it look at it as an array. Okay, so suppose you have a heap A1 all the way to A sub n, where n is the current size of the heap, and I would like to insert a new element. Let me call this new element E. All right, so the basic idea here is as follows. So what we are going to do is we are going to insert, and we are going to come up with a new heap A1 through AN. And what's the most logical place to insert in an array? At the very end, of course. So we are going to do at the very end. In Python, you would do a.append E. But unfortunately, this now is no longer a heap. It does not satisfy the heap property. Specifically, what does it look like in the tree form? So in the tree form, this is the original heap. Be a leaf, all right, and because it has to be a leaf, it now need not be a heap. Okay, it need not be a heap. And specifically, the only way it's going to break is that E is going to be in the wrong relationship with its parent. All right, so as a result, E needs to bubble up. And this is exactly the case bubble up was designed for. If you think about it, here is a heap that's mostly okay, that's mostly correct, and just broken in one place. Broken in one place. If only we could fix that. And simply bubble up has been designed for this, so we will use bubble up. So the algorithm for insert is very, very simple. What is the algorithm? Literally two steps. First step, append. Append E to the end of the heap array. Second step, again, bubble up. At the very last position. So that's it. So append to the end and bubble up. What's the complexity? Well, append to the end is just theta1. It's constant time operation. Bubble up, we already saw, is theta log n. So the overall complexity is theta log n. This is very good complexity. All right. So inserting an element to a heap and maintaining the heap property is really simple. And I don't really need to work out an example. You've already seen how bubble up works, and insertion is just append plus bubble up. That's it. That's it. Okay, as simple as that. All right, then let's move on to the next operation, which is deletion. Suppose I have a heap. Let me say A sub 1, A sub j, A sub n, and let's say I want to delete the jth element. Okay. Now, one of the problems in deleting in an array is I cannot delete in the middle. If I delete it in the middle, then there's going to be a hole. Okay, so if I delete it in the middle, there's going to be a hole, and I don't know how to fill up the hole. On the other hand, I can always delete an array at the end. If I delete an array at the end, I simply readjust the size. So delete at end, is very simple. Readjust the size of the array to n minus 1. That's it. So if you just readjust the size of the array to n minus 1, you're done. You just pretend it's one smaller, and so the array it's now still an array. Okay, it's kind of weird, but it works. So what are we going to do? Here's the idea. When we delete, we are simply going to replace the element we delete with the very last element of the array. Okay, so replace a sub j with a sub n. Second step is adjust size to n minus 1. That's it. Last step is fix what's broken. And how do we fix what's broken? Well, there are two cases here. I either bubble up if a sub, the new element, okay, so if I'm still going to continue calling it a sub n, but let me remember that it's now at the jth position, it's no longer at the nth position, right? This new element a sub n that I brought in is less than its parent. Bubble down if a sub n is greater than its children. All right, one of its children, one or both of its children. So let me simply say greater than its children, and you understand that it can be greater than one or both of its children. You might be wondering, how is this case, or how are each case even possible? Let me give you examples of each case, right? So let's take an example. Okay, so here's an example. I have a heap 1, 100, 2, 103, 110, 213, and I have put this as a tree so that you could visualize it. All right, and let us say my goal here is to delete the element 103. So delete this guy. Off with it, right? So when I delete 103, the last element 3 comes and takes its place. All right, so when that happens, the tree starts to look like this. Okay, so suddenly 3 is in the place where 103 used to be before. So now 3 needs to bubble up. Okay, so even though in an array it looks different, when you view it as a tree, you see it. To fix it, you may need to bubble up. Let me give you an example where you may need to bubble down, right? So what's an example where you may need to bubble down? Okay, so here's the example. I have the heap as an array and as a tree. All right, and let me delete the very root. So let me delete the root. So when I delete the root, then 110 comes up here. So the new heap temporarily becomes, now it's no longer a heap because it's no longer satisfying the min heap property. So it becomes this, and so broken, so bubble down. So we've seen two examples where the new element that comes in, the an that is replacing, may need to bubble up. We saw an example of that. It may need to bubble down. But interestingly enough, it needs to do only one of the two. Okay, it doesn't need to do both. So if I give it an opportunity to bubble up and it just stays in place, then I don't need to bubble down. I need to bubble down. If I give it an opportunity to bubble down, then I don't need to bubble up. So what I simply do is check the element in relation to its parents. If it's in the wrong relation to its parent, bubble up. Check it in relation to its children. If it's in the wrong relation to its children, bubble down. Both cannot happen. Okay, so this is an important thing for you to realize, that both cannot happen. You cannot have a situation where you both need to bubble up and bubble down. Okay, that will be a contradiction. And that's something for you to convince yourself. All right. So what's the complexity of deletion? Well, the complexity of deletion is very simple. It's one swap to adjust size and these are theta 1 operations, and 3 either bubble up or bubble down. In either case, and you don't do both, but in either case it's log n. So the complexity of deletion in a heap is just theta of log n. That's it. So it's also efficient deletion. So you can insert an element, you can delete an element very quickly. All right, very good. The next operation is to find the smallest element in the heap. So how do you find the smallest element in the heap? So if you're given a heap, where is the smallest element? We already showed in a min heap, this is going to be the very first element. Right? So finding the smallest element is very, very simple. Return a of 1. But be careful, I need to have a min heap. Suppose my application required me to find the largest element. I needed to have kept a max heap. Okay, max heap, not a min heap, but a max heap. In a max heap, the very first element would be the largest element. In a min heap, the very first element would be a smallest element. All right. Okay, very good. Now, how do I find the largest element in a min heap? Well, unfortunately, it's not easy to find the largest element in a min heap. It can be anywhere in the last n by 2 elements, I guess. And so you need to do a search. Okay, so not all operations are supported in a heap. So if you have a min heap, then you're very efficient in finding the smallest element, but finding the largest element not so efficient. All right. Likewise, in a max heap, finding the largest element, you're very efficient. Finding the smallest element, not so efficient. Okay. So heaps are not sorted arrays. Remember that. All right. All right. So this is very good. All right. So this gives an application heaps. And this application is to a kind of queue called priority queue. And this is used all over the place, used in many places. Okay. And the important thing to note is this is super useful. And in fact, we will use it as part of other algorithms we will study in this class, which is why this is so important. So what's a priority queue? So what's a queue? So a queue is basically a data structure where you have people arriving, or this could be people, this could be processes, requests, whatever it is, and you store them in an array. And suppose you are able to, new request comes in, request gets processed. So here you would insert, here you would delete, so on. Okay. Now this is easy, and one of the simplest kinds of queue is called a FIFO queue. First in, first out queue. Okay. But sometimes, and this is implemented everywhere. Okay, this is implemented in a lot of places. Most schedulers will implement it, and schedulers are used all over the place. Okay, so most schedulers will implement it. Packet switching, which is also a form of scheduling. So it's used all over the place. Okay, databases. This is used everywhere. All right, this is used everywhere. Now, one variant of the FIFO queue is that, not everything is created equal. So some of them may be high priority and some of them may be low priority, and some of them may be medium priority. So you may have priority levels for each task. Okay, so a new element comes in, it might come in with its own priority level, and you might have priority 1, highest priority, priority 10, lowest priority. You might have a priority number, and you want to process the highest priority ones first, and then the lowest priority ones last. You want to respect the priority. Okay, this is super important in many applications. So in that case, what we can do is we can maintain a heap data structure. Specifically a min heap. If we maintain a min heap data structure, okay, which is simply an array with some special properties, every time a new element comes in, with the priority, let's say priority 8, I'm going to insert the element with the key equals 8 in this heap. Okay, so insert. And every time I am ready to process, I will always take the very first element because it has the lowest priority. It will always have the lowest priority. I will delete it and then restore the heap property by bubbling down in this case. All right. So this kind of a data structure is called a priority queue, and it's a very important application of heap data structures. All right. So the last application I would like to talk about is turning a given array. So suppose I have a random array. I would like to turn it into a heap. Okay, specifically min heap. But if I taught you how to do a min heap, hopefully you know how to do a max heap. Okay, so how do I turn an array into a heap? All right, let's think about this. So suppose I have any given array A. Okay, now how do I make it into a heap? All right, so this is an array of how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. All right, so if I wanted to draw it into a tree, even though it doesn't have the min heap property, I'm hoping to give it the min heap property later. All right, so the idea is really simple, and we will see why this idea works really well. So the idea is really simple. What we do is we are going to move from the very last element of the array to the beginning, move from end to beginning, and bubble down each element. So I will bubble down 9, bubble down 8, 7, 6, 5, 4, 3, 2, 1, bubble down. Okay, and in that process, what I will end up with magically at the end is a heap. All right, let's do this. So if I bubble down 2, if I bubble down starting from the end, I bubble down, then nothing really happens for the first half of the last half of the array. Okay, so if I bubble down, bubble down, bubble down, so if the array is of size 9 or size n in general, then for elements from 1 to n by 2, they have children. But element from n by 2 plus 1 to n, okay, they do not have children. They are leaves. Why is that? Because remember, the left child of an element is twice that element, right? So if n by 2 plus 1's left child would be n plus 1 or more. And so it cannot have a child. Okay, so these elements from n by 2 to n cannot have a children. So for the first half of the array, bubble down is trivial. There's no work. In fact, I don't even need to do this. All right, and then let me come to 4. Okay, so then I bubble down 4. Does anything happen if I bubble down 4? No, because yes, it should, right? Because 4 is in the wrong relation with its children. If I wanted to do a min heap, then what will happen is 4 gets replaced by the smaller of its 2 children. So what will happen is 1 and 4 get swapped. Okay, so the new heap, let me draw the new heap, will become 2, 1, okay, 9, 15, let's leave this part, okay, 7, 6, and then 1, 4, and a 2. All right, very good. So now I have taken care of 4. Now let me bubble down 1. 1 is in the right relation with its children, so nothing happens if I bubble down 1. Let me bubble down 7. 7. Okay, so if I bubble down 7, what will happen is 7 gets replaced by one of its children. So in this case, 1 comes up here, 7 goes down here. Okay, and bubble down is recursive because 7 is still in the wrong relation with its children. It will get swapped with the smaller of its children, like that. Okay, so now 1 comes up here. All right, and finally it's the chance of 2 to bubble down. So when 2 bubbles down, okay, so when 2 bubbles down, I will have it being replaced by the smaller of its 2 children. All right, and that's the final heap. So what's the idea here? The idea is really simple. Let me write down a for loop for I equals n by 2 down to 1. Okay, I don't even do the bubble down for the first n by 2. There's no need to do it. Bubble down a with I. And when I do this bubble down, then at the end of this, a is a heap. Specifically, in this case, the way we are doing it, a will become a min heap. Okay, and that's it. This is the Heapify algorithm. Okay, what's the running time of Heapify? Well, if you wanted to analyze it very simplistically, you could say each of these bubble downs can take up to log n time, and I'm doing it n by 2, so maybe it's n log n. Okay, is that the running time? Well, it is an upper bound on the running time. It is big O n log n. But if I wanted to get a better bound, I need to be more careful. So let me look at the array like this. So if I look at the heap, okay, at the very bottom of the heap, I have n by 2 leaves. Above that, I have at most n by 4 elements at the level above that. Above that, I have n by 8. Above that, I have n by 16. And I keep going until I have 1 element. So this is how a heap is organized. All right. Now, if I'm going to do bubble down here on these n by 4 elements, so if I do bubble down on this n by 2, these are 0 operations. So I don't even bother doing bubble down. If I do it on n by 4, these are all 1 operations. If I do it on n by 8, these are 2 operations, n by 16, 3 operations, and so on. All right. So what's the overall complexity? So you see, not everything hits the worst case. The worst case for this n by 4 is just 1 operation, not log n. Right. So the worst case would be, let me write down the big summation. So it will be 1 times n by 4 plus 2 times n by 8 plus 3 times n by 16 all the way to log n times n by 2 to the power log n. So if you want it to be precise, then this would be summation j divided by n by 2 to the power j plus 1 for j going from 1 all the way to log n. Okay, and this is going to be an exercise for you later on. We can show that this is theta n. All right, so the overall complexity of Heapify is linear in the size of the array. That's it. Okay, instead of n log n, it's simply n. It's proportional, directly proportional to the size of the array in a linear manner. Very good. If we have all of this ready, then we can actually use heaps for sorting to get a very interesting algorithm called Heapsort. Now, what is heap? I would like to sort it in ascending manner. So the steps of heap sort are very simple. first let me heapify the array, make the array into a heap. Okay, and then for I equals 1 to n, let me say the result, let me put the result in a new array, and let's call this the empty array. Okay, let's put the result in the empty array. All right, for I equals 1 to n, insert the smallest element into a of 1 into result. So what you're doing is, now that you have a heap, always take the very first element of the array and delete. And the very first element after you delete is going to be the minimum element of the array, and so at the end of this all, result will become the overall array sorted in ascending order, append into result. All right, so this is the easy version. Now the slightly more trickier version is, I don't want a new result array, so how do I deal with it without creating a new array? Because creating a new array means I have to double up the size of the data. Okay, very simple. Recall whenever I deleted, I took the very last element and I replaced it with the element I'm deleting, and I'm always deleting the first element. So why not reuse the space and simply move a1 back here? So what will happen is, I can now use the deleted portion to store the sorted array. So I'll have the heap at the first part of the array, and the deleted portion, the portion that I'm growing as I delete each element, is going to now become the sorted part. Okay. Now the interesting thing is, this will become sorted in the reverse order, in the descending order, and I can always reverse the array at the end to get an ascending order sort. Okay, not a big deal. What's the complexity? Very quickly, the complexity is going to be, Heapify is theta n. Each of these delete operations would be theta log n. So the complexity would be theta n log n. Okay, and you may object by saying that as I keep deleting, the size of the heap shrinks and becomes smaller and smaller. So this might not be theta log n, but the next step, this would be theta log n minus 1, n minus 2, and so on. But what you will find out that it doesn't make a difference in this case. It's still theta n log n. All right. So this is a very clever sorting algorithm that uses heaps. All right. So we have covered heaps. We have looked at heap operations, bubble up and bubble down in a bit of detail. And then we have, using those operations, we have shown how you can do heap sort and priority queues. All right. Through insert, delete, and heapify operations. And that's the end of this series of lectures on heaps. Hopefully you will be able to code up heaps and understand it. It's a very nice and very elegant data structure that's also extremely useful. Thank you.